Hi, students. In this recording, I'm going to give you examples of how to solve free fall problems where we're applying our mathematical model for constantly accelerated motion to the specific case of free fall. So just as a reminder, and this is, if you remember the last lecture, this is how I remember managing these equations when I was learning physics. Here's our models. So on the left, we have our general model for accelerated motion, which we've discussed a couple of times in previous lectures. Please see previous Zoom recordings for more info. And then on the right, we have our translated mathematical model for this specific case where acceleration is the acceleration due to gravity, and it's the same for all objects on Earth, and that's a value of 9.8 meters per second squared. So every time we see this G, we know the number that stands in for G. G just gives us a shorthand way of not having to write that whole thing. And then we also, in this model, have built in a direction. We have up for positive and down for negative, because we know that acceleration due to gravity is always pointing down towards the ground. We're always being accelerated back to Earth, never, as far as we've experienced, away from Earth. So we're going to follow the same procedures that I have in my example problems for the general use of this mathematical model, where I read the problem and I try to write down the values, the information from the problem in terms of using the variables shown in the equations. So V for velocity, for final velocity, V subscript I, initial velocity or starting velocity, and so on. And then I try to talk myself through what I'm trying to find and what I already know and which equation kind of matches, which equation or equations match those things. So I'll start with, and I'm going to use some of the problems that I've actually assigned as examples so you can work along with me, starting with 41. So 41 states, a construction worker accidentally drops a brick from a high scaffold. What's the velocity of the brick? So velocity equals question mark after 4 seconds. So I know that the time interval is 4 seconds just based on the units. That's part A. And then part B, how far does the brick fall during this time? So how far is distance? So it's asking for the Y value. And again, the time is 4.0 seconds. And this doesn't seem like we know enough. Velocity equals starting velocity minus G times time. G, remember, is 9.8 meters per second squared. So we have that. And the time is 4. But what's that starting velocity? Same problem with equation number 2 for B, for finding Y. Y, sometime later, is equal to starting position plus starting velocity times time. We have that time of 4 minus half times G, 9.8 times time, 4 squared. So in both of these, we need to know the starting velocity and something about that starting position. So there's a key word in this problem. We've discussed some keywords in other problems like how far, meaning distance, how fast, referring to velocity, and how long, referring not to distance but to time. There's a key word like that in this problem, and that word is drops. Whenever a problem or a description uses the word drop, that's indicating that the person or the mechanism of release didn't give the object a starting velocity. It was simply released rather than thrown or shot out of some projectile situation. So whenever we see this word drops, we know that the starting velocity is 0 meters per second. So we actually know more than we think we do. We have this value and this value of 0. So we're almost completely there. The last thing we need to deal with is starting position versus ending position. And if we're not otherwise given a starting position, we can always say that it's 0. So we're just going to define that starting position, the position of this construction worker's hand at the start, as 0 meters. So again, I'll read the problem and then we'll check to make sure we have everything we need. A construction worker accidentally drops a brick from a high scaffold. What is the velocity of the brick after 4 seconds? How far does the brick fall during this time? Okay, so we have the idea of dropping from some place high up, but we're going to define that starting place as 0 meters. We know that the brick falls for a time of 4 seconds. So can we now use the first equation to find the velocity of the brick 4 seconds later to solve part A? So velocity later is what we want. Starting velocity we now know is 0 because of that keyword drop, minus g, but g is 9.8, times time. Time for dropping is 4 seconds. So we've got it. For A, we'll say the velocity of the brick as it is passing 4 seconds later is equal to starting velocity. So I'm here on equation 1, starting velocity minus g times time. I could have left the units out. Everything's in SI units. So velocity 4 seconds later is minus 9.8 times 4. So 39.2 units are SI units of meters per second. Meters divided by seconds squared times seconds gives meters per second. Here, the negative sign just reinforces what we already know. A brick that's been falling for 4 seconds will be going in the downward direction. For part B, we want to know how far has it fallen during this time. So we're going to use the distance equation. So number 2. Starting position, we can define as 0. Starting velocity is 0. So 0 plus 0 times 4. I'll drop the units here to make the math look more obvious. Minus half times g, 9.8 meters per second squared, times time squared. So 0 plus 0 minus half times 9.8 is 4.9 times 4 squared, which is 16. So my answer is negative 78.4 meters. And again, this negative sign tells us what we already know, which is that the brick has dropped below the starting point. The brick has been, quote unquote, dropping rather than having been thrown up into the air. So this is a good example of basic use of the mathematical models for free fall. 42 is a similarly basic application of the mathematical models, but switching your coordinate system to be down positive. Now we're going to look at a problem that is a little bit different. So number 43. And again, we're going to keep our mathematical model nearby so that we can keep referring to the equations. So 43 says a student drops a ball from a window 3.5 meters above the sidewalk. How fast is it moving when it hits the sidewalk? Okay, so how fast is asking us final velocity. We have that keyword drop. So that tells us that the starting velocity of the brick is 0. And then it's a window that's 3.5 meters above the sidewalk. So that means this person has a brick, falls to the sidewalk, and the window is 3.5 meters above the sidewalk. We want to know the velocity at the sidewalk. So I can say sidewalk ending position is y equals 0 meters. Window starting position, y starting is 3.5 meters. Just to say the window is 3.5 meters above, so above being plus, 3.5 meters above the sidewalk. We could also say the window is 0 and that the brick falls 3.5 meters. If I say yi is 0, then I need to say sidewalk y is negative 3.5. But so here are the things we know, right? From reading the problem, here's what we want to know. How fast is the brick going when it hits the sidewalk? So equation number 1 gives us how fast. So this could work. Ending velocity is starting velocity. What we want, we do know this. We do know g, 9.8, but we don't know how much time the brick spends in the air. So one option would be to find the time. Do this in 2 steps. Let's see if number 2 would let us find time. So ending position, we have 0. Starting position, we have 3.5. Starting velocity, we have, and g we have. So it's possible we could solve equation number 2 for time first in 2 steps, and then insert time with what we already know into the first equation and solve for final velocity. But if you remember, the whole point of this third equation is to eliminate the need to know time. So let's see if it works. V ending, that's what we want to know. It's squared, but we can take the square root of whatever answer we get. V starting we know is 0. G we know is 9.8. And starting and ending position we also know. 0 and 3.5 meters. So I can do this in 2 steps, solving number 2 for time, then using that time in number 1, or I can do it in 1 step using equation 3. So being a lazy physicist, I tend to like to do things in 1 step if it's possible. So here I'm going to say that the ending velocity squared is starting velocity squared minus 2 times g times y ending minus y starting. Okay, so I'll leave this v squared over on the left-hand side. 0 minus anything is just minus. So minus 2 times 9.8, which is 19.6, times 3.5, but times negative 3.5. So minus times a minus is a positive, 68.6. That's good that we don't have a minus here anymore because we're going to have to take the square root of both sides to find velocity. And if we ended up with an imaginary velocity, that'd be a good indication that we did something wrong. So square root of v squared equals square root of 68.6. Whenever I take the square root, I have 2 answers, positive or minus. And I don't know where the square root button on this calculator is. This is not my usual calculator. There it is. There. So plus or minus 8.2825, blah, 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 around to 3 digits, meters per second. And that plus or minus has a physical meaning, right? Up is positive, down is negative. We know that a brick that's been dropping 3.5 meters is going in the downward direction. So we select the negative answer to this square root because we know the direction is downward. So there are 2 examples of using the equation model for free fall motion to solve problems. So try the rest, and then at the start of class on Monday, I'll answer any questions you've come up with. I'll make sure you have answers to check, and we'll review problems, answers Monday before the quiz.